Today we're going to look at an interesting integral that, well, the lore behind it says that it was from an 1886 exam at the University of Cambridge. It's also featured in a pretty well-known book called Inside Interesting Integrals. And, well, in fact, that's where I saw it. And the solution, well, we're going to take some of it from, well, the solution inside of that book, although not all of our solution. So let's see what we've got here. We want to calculate the integral from 0 to 4 of the natural log of x over the square root of 4x minus x squared dx. And we're going to do some preparatory results first, just to streamline our final solution. So we're going to start by finding the integral from 0 to 1 of dx over the square root of x minus x squared. Okay, so I've got that integral up here, so that's good. We're all set. So now what I'm going to do is multiply the numerator as well as the denominator of this by 2. So let's write the 2 in the numerator out front, and then the 2 in the denominator we will bring inside of the square root. But bringing it inside of the square root means that we have to square it, turning it into a 4. So that's going to give us 1 over the square root of 4x minus 4x squared dx. And you might say, well, why did we do that? Well, it's just going to make the completion of the square, which is about what we're going to do, or what we're about to do, inside of the radical a little nicer. Okay, so next up, what I'd like to do is add and subtract the number 1. In other words, we're going to do mathematicians' favorite trick of adding 0. And we're doing that under the radical. So here we're going to have the square root of 1 minus, and then all of this is in parentheses, 1 minus 4x plus 4x squared. Then we've got this dx as well. So observe that the 1 and the 1 sort of obviously cancel. The minus sign flips that minus sign in front of the 4x to a plus, which is how we see it above. And then it flips the sign in front of the 4x squared into, well, a minus, which is, again, how we see it above. But now observe that we've got something that is a perfect square binomial inside of those parentheses. So let's do a little factorization here. So I'm just going to rewrite a bunch of the stuff. And now in the square root, we have 1 minus 2x minus 1 quantity squared. And then, well, we've still got a 1 in the numerator and then dx. Okay, great. So now upon examining this integral, I think its current structure motivates a fairly standard substitution. It's a trigonometric substitution. So let's take the substitution 2x minus 1 is equal to the sine of theta. Okay, well, notice that that means that 2 dx is equal to cosine of theta d theta. Oh, but check it out. Over here, we've got a 2 times dx. So in fact, this 2 times dx is exactly cosine of theta d theta, given the substitution that we're doing. So that's pretty nice. And then, well, what about the bounds of integration? Well, notice that if x is equal to 0, well, that tells us that the sine of theta is equal to -1, but that tells us that theta is minus pi over 2. And you might say, well, there are a bunch of places where sine of theta is equal to -1. But if you recall, generally when we do this substitution with x equals sine theta, or something like x equals sine theta, like we have right here, our values of theta are constrained between minus pi over 2 and pi over 2. That's where this thing is 1 to 1. Okay. Then observe that if x is equal to 1, that leads to sine of theta equals 1, which in turn leads to theta equals positive pi over 2. Okay, so there we did it. We changed the order, or we changed the bounds of integration as well. So now we're going to have the integral from minus pi over 2 to pi over 2. And then, well, like I said, that dx is our cosine theta d theta. But given that 2x minus 1 is sine theta, observe that this stuff inside of the radical is 1 minus sine squared theta. But of course, that's equal to cosine squared theta. But then we take the square root of that and we get, well, it's technically the absolute value of cosine theta. That being said, since we're on the region between minus pi over 2 and pi over 2, that's in fact simply equal to cosine of theta. But we've got one of those in the numerator as well as the denominator. Those will cancel, leaving us simply with a d theta. But we're integrating d theta from minus pi over 2 to pi over 2, so we simply get the length of the interval, which is pi. So that means we can fill this over here in with pi, and, well, we've got our first tool. And now we're moving on to our second integral that will serve as part of our solution, which is the integral from 0 to pi over 2 to the natural log of sine of x dx. So in fact, we did this integral on the channel a really long time ago, and you can in fact do this a couple of different ways. But since this is only part of our solution, we're going to do this in kind of a crazy streamlined method. Okay, so let's start with our integral up here, and I'm going to rewrite this, well, in a seemingly crazy way. So I'm going to write this as the integral from 0 to pi over 2 of the natural log of sine of x dx. Okay, well, nothing happened there. And then I'm going to add another copy, so integral from 0 to pi over 2 of, well, it's again, like I said, another copy, so natural log of x sine of x dx. And then I'm going to subtract a copy as well, because, well, if I added a copy, well, then I definitely have to subtract a copy. Okay, so there we've got that. And now I'm going to perform a substitution on each of these copies that were, well, one of them was added and the other one was subtracted. So let's color code this a little bit here. So I've got this pink underline, and I'll put a pink box here to just say that that's where we're going to do this substitution. Okay, so what I'll do here is take, let's say t, and set it equal to pi over 2 minus x. We'll observe that that's going to make dx equal to minus dt. Now, when x is equal to 0, that means that t will be pi halves. And then when x is pi halves, well, clearly t is going to be equal to 0. And then furthermore, let's notice that the sine of pi over 2 minus t is equal to the cosine of t. That's a well-known identity. But that's simply what we get, from inverting this t equals pi over 2 minus x. Okay, so let's put a little box around that and then make our substitution. So obviously we have to bring this first integral down. We're not doing anything with that. So we've got the integral from 0 to pi halves of natural log of sine of x dx plus, well, this thing that we just changed. But now the integral is going to go from pi halves to 0, and it'll be natural log of cosine of t. Oh, but then it's going to pick up this minus sign. Well, let's use that minus sign to flip the order of the bounds of integration back. So in fact, what we'll have here is the integral from 0 to pi over 2 of the natural log of the cosine of t and then dt. And let's see. Now we've got to talk about what's happening with that next substitution. So let's put a little bit of a blue box here to, just indicate that we're making that substitution over there. And for this next substitution, we're going to set u equal to x plus pi over 2. Of course, that means that x is equal to u minus pi over 2. Okay, but now notice that that means that dx is simply equal to du. If x is equal to 0, that means that u is equal to pi over 2. And then if x is equal to pi over 2, that means that u is equal to pi. Okay, then one last thing. Let's observe that the sine of u minus pi over 2 is equal to the sine of u. And well, this is definitely not always true, but it is true for this region where we're doing the change of variables. That is, we're shifting from the interval from 0 to pi over 2 to pi over 2 to pi. That's because the sine function is symmetric about that line, which is, x equals pi, or the vertical line at pi over 2, I should have said. Okay, so let's put a little box around that and then rewrite our integral over here. So notice that's simply going to turn into minus the integral from pi over 2 up to pi of the natural log of the sine of u du. Okay, great. So next up, what I'm going to do is push these two first integrals together. So let's see, that's going to end up giving us the integral from 0 to pi over 2 of the natural log of the sine of x times the cosine of x dx. And you might say, well, one of those integrals is with respect to t and one is with respect to x. Well, what we're doing here is a simple like substitution of the dummy variables. So we'll just switch that t back to x. And then we're going to bring this second integral down, or this third integral down in kind of a crazy way. Well, we just showed that this blue underline is equal to this second integral, but we're going to bring them both down with a coefficient of 1/2, so they'll clearly sum to what we had before. So in other words, we're going to have minus 1/2 times the integral from 0 up to pi over 2 of the natural log of the sine of x. And then after that, minus 1/2 times the integral from pi over 2 up to pi of, well, it's going to be another natural log of sine of x dx. Okay, great. And then let's see what we can do over here. Well, we're going to use a product to sum formula on this sine times cosine to rewrite it as the sine of 2 times x over 2. I think that's a well-known identity. And then we'll use logarithm rule to change that quotient to a difference. So let's see. We're going to be left with, well, let's maybe put the minus out front. So it's going to be minus, let's see, the integral from 0 to pi over 2 of the natural log of 2 dx, and then plus the integral of the natural log of the sine of 2x dx minus, now let's push those two together because observe that the ending point of one is the starting point of the other, so we can push that into 1/2 the integral from 0 to pi of the natural log of the sine of x dx. Okay, great. But now we're actually almost done. Let's observe that this first one is going to turn into minus pi over 2 times the natural log of 2. And then after that, well, let's perform a change of variables on, well, perhaps this third integral. So let's maybe fit it in over here. So let's see if we can do that. And this is going to be a very simple change of integral or change of variables. Let's say we have x is equal to 2 times u. But observe that that means that dx is equal to 2 du. If x is equal to 0, that tells us that u is equal to 0. If x is equal to pi, that tells us that u is equal to pi over 2. We'll observe that this 2 that we pick up from the dx is going to cancel this half out front. And then, well, let's go ahead and bring this down so that we're ready. Integral from 0 to pi over 2 of natural log of the sine of 2x dx minus, like I said, the 2 and the half cancel, and we're left with the integral from 0 to pi over 2 of the natural log of the sine of 2u du. But those are exactly the same integral, simply with a different dummy variable. So that means that these two are most definitely going to cancel, leaving us with the value for our second integral tool. So let's put that over here. We just showed that this was equal to minus pi over 2 times the natural log of 2. Okay, so both tools are engaged, and now we're ready to finish this thing off. So we're going to start with a substitution. And I think this substitution is non-obvious. That being said, it works really nicely. So we're going to take x and set it equal to 4 times y. But observe that that means that dx is 4 dy. It also means that the bounds of integration change. If x is equal to 0, well, pretty clearly y is equal to 0. If x is equal to 4, well, y will be equal to 1. Okay, so there we have it, our change of variables. So let's see what that leaves us with. So immediately we have that this is 4, and then the integral from 0 to 1, the natural log of 4 times y over the square root of 16y minus 16y squared dy. So observe that 4 times 4y is obviously 16y, and then 4y quantity squared is 16y squared. Okay, well, the next thing that we can do is factor a 4 out of that square root, which is in the denominator. But that means we've got to take the square root of it, but that's going to cancel the 4 that we have out front. So let's do that simultaneously with splitting this natural log of 4 times y into the natural log of 4 times the natural log of y. So that's going to leave us with the natural log of 4 times the integral from 0 to 1 of dy over the square root of y minus y squared. And then, let's see, plus the integral from 0 up to 1 again of the natural log of y over another square root of y minus y squared dy. Okay, nice. Now, let's maybe look for a substitution for this second integral right here. So let's work that substitution down in this blue box. And the substitution that works here is we'll take y and we'll set it equal to the sine squared of theta. But now let's observe that that means that dy is equal to 2 times sine theta times cos theta d theta. Okay. Then when y is equal to 0, that means that theta is equal to 0. When y is equal to 1, that means that theta is equal to pi over 2. I think that's all pretty straightforward. Then furthermore, well, we know something about this right here because we did our calculation. Observe that that's simply the natural log of 4 times pi. So let's just bring that down as is. So we'll have pi times the natural log of 4. And then we'll have plus our integral from 0 to pi over 2. And then we'll have the natural log of sine squared. So let's write that, natural log of sine squared of theta. And then we'll have our dy component, which will bring a 2 out front from this 2. And then we'll have the sine of theta times the cosine of theta d theta. And then let's see, what's going on in the denominator? So if y is sine squared, then the square root of y minus y squared, well, you can pretty quickly check that that is going to give us the sine of theta times the cosine of theta. But we get a ton of simplification at this point. Observe that this sine will cancel this sine, this cosine will cancel this cosine, and then we can take this 2, which is inside of the natural log, well, it's the square of the sine inside of the natural log, and use logarithm rules to turn that into a 4. And then, well, notice we've got the integral from 0 to pi over 2 of the natural log of sine theta d theta, which we have a value for. But we've got a 4 out front, so let's multiply it by 4, leaving us with pi times the natural log of 4 minus 2 times pi times the natural log of 2. Oh, But look what we can do here. We can take this 2, bring it inside the natural log to a square, and we've got pi natural log of 4 minus pi natural log of 4, but that's simply equal to 0. And there we have it. We've evaluated, well, this very, very old exam integral. Well, it's got a value of 0. And that's a good place to stop.